right now, the AI writing your emails or like generating your code isn't just floating around in some magical weightless cloud.
Right. Yeah, it's definitely not.
I mean, it is physically trapped inside a massive, sweltering warehouse. It's burning through insane amounts of electricity and hitting a brutal speed limit dictated by the literal speed of light.
It really is the ultimate reality check, honestly. We love to use ethereal words like, the ether or the cloud.
Yeah, because it makes the technology feel like pure, unconstrained thought, right?
Exactly. But the reality is that artificial intelligence is completely bound by physical distance. I mean, the distance between microscopic transistors and like the exact length of the copper cables connecting them.
So welcome to today's deep dive. Our mission today is to decode this fascinating and honestly completely brutal technical memo that we got our hands on.
Yeah, it's a harsh read, but a really important one.
Totally. And this memo is aimed at an analog circuit designer, the kind of engineer drawing microscopic wires on a computer chip. But we are going to use it to zoom all the way out.
Right, tracing the path from those invisible wires all the way up to sprawling city-sized data centers.
And along the way, we're going to uncover the surprising physical bottlenecks that are literally dictating the entire future of AI. So for those of you listening who want the deep aha moments without, drowning in information overload, you are in the exact right place.
Absolutely.
Okay, let's unpack this. Our source material describes the physical architecture of AI hardware as a matryoshka doll.
Yes, the nested Russian dolls. It's a brilliant way to visualize it because it immediately shatters the illusion that an AI is just like one big computer.
Right.
It's not. It is a deeply nested 5-layer system. And if you want to understand why AI is currently hitting a massive wall, you have to understand why we are forced to build these layers, starting from level 1 all the way up to level 5.
So let's figure out why the dolls exist at all. I mean, my first question when looking at this was, why not just build one giant, super fast level 1 chip?
I mean, that's the dream, right?
Yeah. Why can't we just make a processor the size of a dinner plate, put it in a metal box, and call it a day?
It's a great question, and the answer comes down to manufacturing yields and thermodynamics.
Oh, thermodynamics, sure. Things get hot.
Very hot. When you are printing billions of microscopic transistors onto silicon, imperfections happen. If you try to print a chip the size of a dinner plate, and there is a single microscopic dust particle or defect anywhere on it,
The whole thing is ruined.
the whole plate is ruined. You just have to throw it away. Plus, a chip that big would generate so much concentrated heat, it would literally melt itself into slag.
Wow, okay. So instead of one giant piece, we are forced to chop the silicon up into tiny manageable pieces and string them together.
Exactly. Which brings us to the smallest Russian doll, level 1 or L1.
Right, L1, the chip.
Yeah, L1 is the chip, the die, or the system on a chip. This is the single piece of silicon where the actual math happens.
The calculator.
Right, it contains the arithmetic logic units, the ALUs, which are the calculators, and it contains incredibly fast memory called SRAM.
And those are physically super close to each other.
Very close. At this L1 microscopic level, the calculators and the memory talk to each other using what's called a network on chip. The communication here is practically instantaneous because the physical distance is measured in millimeters.
Okay, but because we can't make that chip the size of a dinner plate, we have to move up a size to L2. We have to connect it to other chips.
Exactly. L2 is the module, or the card. Think of like an NVIDIA H100 PCIe card you might slide into a desktop computer.
Right, the bulky thing with the fans.
Yeah, you take that L1 chip and you mount it on a circuit board. To communicate at this layer, you are using printed circuit board wiring, or a microscopic bridge called an interposer.
An interposer.
Yeah, it's basically a high-density superhighway connecting two chips side by side. It's a bit slower than staying entirely on L1, but you're still dealing with raw electrical signals traveling over very short, very fast physical connections.
Okay, so that's L2. But one card isn't enough to run ChatGPT, so we step up to the next doll L3, which the source calls the node.
The L3 node is essentially a single server chassis, a physical metal box.
Just a standard server box.
Right. Inside this box, you have a central CPU, your main system memory, and multiple L2 cards. For example, the current industry standard is packing 8 massive GPUs into a single L3 node.
So they're all cramped in this one box together.
Yep. And to get these 8 GPUs to talk to each other, they use incredibly fast, dedicated pathways, like NVIDIA's NVLink.
NVLink, okay.
Yeah, NVLink is basically a private, high-speed rail network explicitly designed so these 8 chips can share data back and forth as if they were one bigger brain.
Wait, so if I pack 8 GPUs into an L3 node, what happens when my AI model is so big I need 100 GPUs or 1,000? Do I just start stacking these L3 metal boxes on a shelf? Is that L4?
That is exactly what L4 is, the rack. It is a large metal cabinet holding many L3 nodes, stacked like pizza boxes.
Right, I've seen pictures of those data centers.
Yeah, but here is where the friction begins. At L4, these boxes can no longer use that private NVLink high-speed rail.
Why not?
Because they're in different boxes now. To talk to a box above or below it in the rack, they have to use standard network cables and external switches, utilizing networking protocols like InfiniBand or Ethernet.
Which finally brings us to the biggest all, L5, the cluster.
The cluster is the whole sprawling system. Row after row of these L4 racks, containing tens of thousands of GPUs, networked together across a massive warehouse using miles and miles of high-speed optical fiber.
To help you visualize the sheer mechanics of this at home, let's use an analogy. Because, it's not just about how big these areas are. It's about the friction of moving things between them.
Right, the transit costs.
Yeah. So think of L1, the chip, as you grabbing a file off your own desk. It's instant. L2, the card, is sliding your chair over to your coworker's desk to hand them a file.
Still very fast.
Right. L3, the node that server box with 8 GPUs is like taking the elevator to another floor in your building. But crossing into L4 or L5, that is entirely different. That's like having to put your file in a cardboard box, hire a FedEx truck, drive it across the state, and wait for someone to sign for it on the other end.
That FedEx analogy perfectly captures the friction of transit.
Yeah.
And it's crucial to realize that when you type a prompt into an AI right now, the model analyzing your text is far too large to fit on your L1 desk or even in your L3 building.
Yeah, it's massive.
Exactly. You are dispatching thousands of FedEx trucks across the entire L5 country to get your answer, and you don't even realize it.
But out of all these layers we just walked through, this memo we're analyzing zeroes in on one specific boundary as the absolute ultimate battleground. It focuses entirely on L3, the node.
Yes.
The edge of the server box, the edge of the building. Why is crossing the border of an L3 node such a catastrophic problem for hardware engineers?
Because that border represents a fundamental shift in the physics of how data moves. The core technical conflict the source drills into is node-to-node communication overhead.
Node to node.
Right. The physical casing of that L3 server matters immensely because the moment your data leaves that box, the path of the electricity literally changes.
It's a completely different medium.
Yes. Let's look closely at intranode communication staying inside the L3 server. Those 8 GPUs are talking over NVLink. It's raw, unadulterated electrical signaling.
The private high-speed rail.
Exactly. It's a dedicated private highway just for them. The bandwidth is massive, and the latency and the time it takes a signal to start and stop is nearly non-existent. It is blazingly incredibly fast.
But internode communication leaving the L3 box to talk to a GPU in another rack?
That's where the penalty hits you like a brick wall. To leave the L3 box, your data can't just be raw electricity flowing down a private wire anymore. You are entering a shared network switch, like InfiniBand.
Ah, okay.
You are sharing the row with millions of other data streams from other racks.
So you have to manage the traffic. You can't just blast signals everywhere.
Precisely. If you just blasted raw electricity into a shared network, it would crash into someone else's data and corrupt everything. So before your data leaves the node, it has to be chopped up into tiny pieces.
Which they call packetizing, right?
Yeah, it has to be packetized. The system has to slap a literal digital barcode and a routing address onto every single piece. It has to follow complex network protocols to ensure it arrives safely, and then it has to be unpacked and verified on the other side.
Which takes time.
An unbelievable amount of time in computing terms. This protocol overhead is devastating. The source makes it crystal clear the exact moment you cross that L3 boundary, your processing speed drops by a full order of magnitude. We're talking 10x slower, or worse, the latency spikes drastically.
Wow. So if intranode communication, staying inside the box is like driving a Formula One race car 200 miles per hour on a private, perfectly paved racetrack.
Yeah.
Internode communication is like being forced to exit the track, stop at a toll booth, put your race car inside a shipping container, fill out a stack of customs paperwork, and put that container on a public freight train.
That is exactly what it's like.
No wonder system designers absolutely hate it. You build this microscopic, miraculously tuned race car of an L1 chip, and then you spend 90% of your time waiting for a literal digital freight train.
What's fascinating here is that this exact physical bottleneck, this dreaded node wall, completely dictates the wildly different strategies of the biggest companies in AI hardware today.
It's not just a minor inconvenience.
Not at all. This isn't just some abstract speed limit for engineers to debate. This single physical barrier determines the survival and the valuation of billion-dollar tech giants.
Let's look at how those giants are fighting the node wall. The memo highlights Grok, which is famous right now for having unbelievably fast processing speeds for AI inference, and it contrasts them with NVIDIA, the undisputed heavyweight champion of AI hardware.
Two very different approaches.
Very. Let's start with Grok. The source talks about the cruel truth of their approach.
Right. Grok uses an SRAM-based architecture. If you recall L1, SRAM is that incredibly fast memory located right next to the calculator on the chip.
Okay, so it's close by.
Yeah, in our analogy, it's like having a chef's cutting board right in front of you. You can chop vegetables instantly. Grok chips rely almost entirely on SRAM, which is why their processing speed is blistering.
But there's a catch.
A big one. Here is the cruel truth in hardware physics. SRAM takes up a massive amount of physical real estate on the silicon.
So it's incredibly fast, but the capacity is tiny. If you want more ingredients, you can't keep them on the cutting board.
Exactly. A single Grok chip can't hold a massive modern AI model. In fact, a whole L3 node of Grok chips can't hold it.
Oh, wow. So it's really small capacity.
Yes. To run the massive models powering today's AI, Grok is physically forced to string together many, many L3 nodes.
Meaning they're forced to constantly exit the racetrack and use the freight train.
Yes. And the source points out a brutal reality for system architects. If your design requires you to constantly hit that slow L4 to L5 communication wall between nodes, the lightning-fast speed of your individual SRAM chip gets entirely swallowed up by the networking delay.
It just doesn't matter how fast the chip is anymore.
Exactly. The memo uses a harsh phrase. It calls the blistering speed of the Grok chip mere statistical noise compared to the massive delays of internode communication.
Statistical noise. Ouch.
Right. Think about it. It doesn't matter if your race car can go 200 or 500 miles per hour if it spends 99% of its day sitting in a shipping container waiting for a switch to route it.
Wow. Calling someone's cutting-edge, billion-dollar processor statistical noise is a ruthless way to describe hardware physics.
Very ruthless, yeah.
But then the source pivots and contrasts this exact problem with NVIDIA's strategy, specifically looking at their new Blackwell architecture, the NVL72. And the memo calls what NVIDIA did here a total masterstroke.
Because NVIDIA looked at the node wall, that toll booth that slows everything down, and they didn't try to build a faster freight train.
They didn't try to optimize the network.
No. They realized the toll booth itself was the enemy. So instead of trying to make networking better, they physically expanded the definition of the L3 node.
They just moved the city limits so they wouldn't have to cross the border. But, how do you physically do that? You can't just wish a node to be bigger.
No, you have to physically build it. The NVL72 integrates an entire L4 Rack 72 heavy-duty GPUs and wires them all together not with network cables and InfiniBand switches, but with massive, heavy copper backplanes.
So it's all wired like one giant board.
Exactly. They physically connected 72 GPUs so that electrically they all think they're sitting on the exact same motherboard inside a single L3 node.
That's insane.
It is. By doing that, they bypass the packetization process entirely. They turn what used to be a slow, heavily regulated internode network communication into a fast, raw, intranode private highway. They essentially built a rack-sized racetrack to erase the protocol overhead.
Here's where it gets really interesting, though. If NVIDIA's brilliant solution to the node wall is just to build a physically bigger node to stretch out that private copper racetrack,
Yeah.
why stop at a rack? I mean, why not make the entire L5 cluster one giant L3 node? Why not wire a whole sprawling data center together with copper backplanes so it acts as one giant computer? What is physically stopping them?
The literal laws of the universe, specifically propagation delay and the speed of light.
Okay, speed of light.
The source notes this explicitly when challenging the designer to understand physical limits. Even raw electricity in a copper wire or optical signals in a glass fiber do not travel instantaneously. In the cables used in these massive data centers, signals propagate at roughly 2/3 the speed of light in a vacuum.
Which to a human sounds incredibly fast. 2/3 the speed of light.
It sounds fast to us, yes.
Right.
But you have to think like a computer operating at gigahertz frequencies, trying to execute billions of calculations every single second.
Right, their perception of time is totally different.
Exactly. At those processing speeds, the sheer physical length of a 10-meter cable running across a room introduces an unavoidable, highly disruptive delay. You wait for the light to arrive, and your processor sits idle.
It's literally waiting on the speed of light.
Yes. You can only physically expand a copper node so far before the time it takes the electrical signal to physically travel from the top of the rack to the bottom of the rack becomes the new bottleneck. You can optimize protocols all you want, but you literally cannot cheat physics.
Okay, so these absolute unbreakable physical limits, the physical size of SRAM on the silicon, the packetization toll booths, the literal speed of light traveling down a fiber optic cable, they dictate corporate strategy for giants like Grok and NVIDIA.
They absolutely do.
But the memo we are analyzing today isn't written to Jensen Huang at NVIDIA. It's written to an analog circuit designer, a guy whose job it is to sit at a desk and draw microscopic wires on a tiny L1 chip. Let's look at the tough love portion of this source because the author gets intensely personal.
It is a phenomenal teardown. The author of the memo accuses this analog designer of having a massive blind spot.
A blind spot.
Yeah, the designer apparently asked a seemingly innocent, highly technical question about how to define the boundaries of a node in his software, and the author pounced on it, saying that the question itself reveals a total failure of imagination.
The exact quote is, "Saying you don't know what a node is proof you are working without being conscious of how the circuit you're designing will ultimately be used." That is a direct hit to the ego.
Oh, totally. The author is essentially grabbing the engineer by the shoulders and saying, you are obsessing over your tiny microscopic circuit, totally failing to see that that single signal line you are drawing right now might eventually connect to thousands of kilometers of optical fiber across an L5 cluster.
Right.
If you don't understand the physical distance and the friction your signal will face after it leaves your chip, you are failing at your fundamental job as an engineer.
The source doesn't just insult him, though. It lays out a very specific 3-step action plan for this engineer to fix this blind spot.
Correct. Priority 1 is gaining a macro view. The memo tells the designer to stop looking at his microscopic chip design software, a program called Cadence Virtuoso.
Just stop using it.
Yeah, the author says just close the program, stop staring at it. Instead, go log into Google Cloud or AWS topologies. Look at the real-world macro blueprints of how thousands of GPUs are actually connected in physical data centers.
It's like telling a plumber to stop staring at the trap under one sink and go look at the blueprint of the entire 100-story skyscraper to understand water pressure.
Precisely. You have to see the whole system. Priority 2 is reevaluating physical limits. The memo challenges the designer to sit down and scientifically calculate the difference between the electrical delay on his microscopic chip wiring versus the physical propagation delay of a signal moving at 2/3 the speed of light through miles of network cables.
Forcing him to do the math.
Exactly. The goal is to force the designer to do the math himself, so he understands in his bones just how much system architects utterly despise communication outside the node.
Because to a system architect, communication equals delay. Every time data moves, it slows down.
Yes, every single time.
And that leads to priority 3, which is where the memo gets almost existential. Career pivot.
Yes. The memo tells the designer to stop calling himself an analog circuit designer. The author argues that title is far too narrow for the modern era.
Too specialized.
Way too specialized. Instead, the engineer needs to rebrand his market value and his entire mindset as an expert in the physical layer supporting ultra-high-speed interconnects.
Okay, I have to push back here on behalf of you, the listener, and honestly on behalf of that poor engineer who just got a massive reality check dropped in his inbox. Is it really fair to attack an engineer for just doing his highly specialized job?
I mean, it seems harsh.
We are told constantly in the modern tech industry to specialize, to find our tiny niche and master it. Why is this author so aggressive about zooming out?
It's a very fair question to ask. But if we connect this memo to the bigger picture of where AI is going, the author is highlighting a profound and systemic danger in modern technology. Hyperspecialization can actually be a trap.
A trap? How so?
Because the most difficult, multi-billion-dollar problems in AI today are not solved in isolation at L1 or L3 or L5.
Right.
The friction, the bottlenecks, the massive speed limits, they all happen at the seams. They happen at the boundaries between the layers. If you only understand the microscopic chip, you might design a brilliant piece of silicon that utterly fails the moment it's plugged into a massive data center because you didn't account for network latency.
It works in theory, but not in the real world.
Exactly. The true value, the real market power and engineering breakthrough lies in understanding the entire L1 to L5 stack. You have to understand how the microscopic intimately interacts with the macroscopic.
Which is exactly what you are doing right now by tuning into this deep dive. You are actively zooming out. So let's concisely recap this incredible journey we've taken today, because we covered a lot of physical and conceptual ground.
We really did.
We started with the realization that AI is not ethereal magic floating in the sky. It is a physical, heavy matryoshka doll made of L1 chips, L2 cards, L3 nodes, L4 racks, and L5 clusters.
And out of all those nested dolls, the L3 node is the ultimate bottleneck, because the moment data crosses that physical boundary, it is forced to change paths.
It hits the toll booth.
It has to be packetized, managed by complex protocols, and severely delayed.
It goes from the private 200-mile-per-hour racetrack to the public freight train. And that single physical reality dictates everything we see in the market today.
It really does.
It's the reason Grok's blistering fast SRAM chips get hopelessly bogged down in internode traffic. It's the exact reason NVIDIA went to the massive expense of physically expanding the size of their node, using heavy copper to encompass an entire rack.
To avoid the toll booth entirely.
Right, and it is the reason why an engineer drawing microscopic lines on a screen desperately needs to understand the physical topology of a massive cloud data center.
So what does this all mean for you?
Yeah, why does it matter? It means that the next time you hear a tech company pitching their shiny new cloud AI, or the next time you read a headline about a massive leap forward in artificial intelligence capabilities, I want you to immediately picture the massive physical infrastructure behind it. Picture the heat sinks, the heavy copper backplanes, the miles of optical fibers, and the absolute unbreakable speed of light limitations that are barely holding the whole thing together.
And understanding those physical limits raises a profoundly important question, something we haven't directly discussed today, but that naturally flows from all this source material.
Oh, what's that?
We all know that AI models are continuing to grow exponentially in size. Every single year, they demand more compute, more memory, and vastly more data to train.
They just keep getting bigger.
Right. But as we just learned, our hardware communication speed across these sprawling physical nodes is strictly bound by the speed of light. We cannot make light travel through a fiber optic cable any faster than the laws of physics allow.
Unless we break physics, which we can't do.
Exactly. So if models keep getting bigger and communication delays keep stacking up as we string more and more nodes together, are we hurtling toward an inescapable physical plateau? Will the future of artificial intelligence require us to eventually stop trying to build ever larger sprawling L5 clusters and instead force us to completely rethink how AI thinks on a much smaller, more efficient scale?